So are there any major differences between what's on a cell phone or another mobile device and a computer in terms of how the computer architecture and the hardware works?
Well, Khari, that's actually a great question. In 2018, I did a sabbatical at Google with a group looking at silicon for these kinds of things. And I thought, what do I know about these kinds of things? Because I've never operated in this space. I've only operated it with big computers. But I had operated with big computers for, actually almost 30 years at that time. And so these devices have grown up to be real computers. So they have all the standard components of compute, interconnect, memory, and storage. But they have them in different proportions, and they have this abundance of accelerators, which classical computers have not had at this point, but I think will going forward. There was a recent Apple iPhone that had 42 accelerators.
So prior to the iPhone with the 42 accelerators, what was a typical number for a phone to have?
Right. So typical is hard to say because they were changing pretty fast. But if you look at a series of Apple iPhones from 2010 to 2016, the number of accelerators went from 9, 12, 17, 22, 29, 31, 36. You can see climbing fast.
Wow. So are most of these accelerators being used for things like the video processing you gave in your example, or is it a wider variety of functions?
It's a wider variety of functions so that in any given use case, like recording video, you are not using 42 accelerators. You're using a relatively small number, like 5 or 7. But presumably these were all put on there because there's some important use case that needs them. But one of the things that I think we need to evolve is some of this stuff is put on there, and maybe when you put it on the chip, you don't know quite what the phone's going to be used for when it comes out. And so you might put things on unnecessarily. I think we need a better science for designing chips with multiple accelerators and accelerator level parallelism. We tried to help a little bit with a model called Gables.
Could you discuss the Gables model? What is that?
Okay, so when you have a chip with 42 accelerators, how do you decide which ones to have and which ones to select and, how to size them and things like that? It's just very complicated. So it'd be nice to have a simplified picture to get a first answer, not a final answer. And so Gables was our attempt to do that, and it builds on something called roofline. So the roofline model was for a homogeneous multi-core chip, which is a chip that every processor core is the same. Mm-hmm. And it modeled the chip with a peak computation performance and a peak off-chip communication bandwidth in a plot that looks like a roofline. And so what Gables did is said, well, we can't model our 42 accelerators that way, but we can perhaps do a roofline for each accelerator because each accelerator is different, they're heterogeneous, and then find a way to combine them to model the whole chip. And that's what Gables does. And Gables gets its name by a roof that has many roof lines.
Okay. So have you used this model on any products or technologies that have shown promise?
I have not used it on products. However, I'm aware of at least 2 instances, one where it was incorporated in the tool chain of a major tool provider. I'm not sure I'm allowed to say the name. And I know it was used for the preliminary development of some products at a major IT company. And they're still using it, but I think that's confidential. But I will say, I think it's better than the community thinks it is at this point, because it's not like, super popular.
Well, yeah, maybe now people will think more about it. Anything else you want to say about the Gables model?
I'll just say this, that I think it's important when you encounter a complicated system to try to figure out a way to get your head around it. And, Gables was our attempt to do that. And I think that model, it even has value if you don't believe the numbers, because it gives you a way to frame your thinking about the system and pay attention to these communication and these performance things and how they interact. And that's valuable even if you don't believe the output of the number.